Ground is defined as a conducting connection, whether intentional or accidental, between an electrical circuit or equipment and the earth, or to some conducting body that serves in place of the earth. Grounded means connected to the ground or to a conducting body that extends the ground connection. Grounding is the act of connecting a system or circuit to ground. Equipment grounding is the grounding of non-current carrying metal parts of equipment, enclosures, and raceways. System grounding is the intentional grounding of part or all of a system or circuit to maintain a predetermined voltage relationship between the system and ground. Neutral is the midpoint of a three-phase transformer secondary or generator winding. A neutral conductor is a conductor connected to the neutral point of a system and intended to carry current only under fault conditions. A ground conductor, also known as a grounding electrode conductor, is a conductor used to connect equipment or the grounded circuit of a wiring system to a grounding electrode. A current-carrying conductor is a conductor intended to carry current in normal operation. A non-current carrying conductor is a conductor not intended to carry current in normal operation, but may do so under fault conditions. Earth means connected to the earth or to a conducting body that serves as an earth electrode. Bonding is the intentional electrical connection between two or more conductive parts. A grounding rod is a metal rod driven into the ground and used as a grounding electrode. A grounding plate is a metal plate buried in the ground and used as a grounding electrode. The recommended maximum resistance for a single ground rod is 25 ohms. For two grounding rods, the minimum distance apart is 6 feet. For three grounding rods, the minimum distance apart is 10 feet. If the required resistance cannot be achieved with one rod, multiple rods may be used. According to the Philippine Electrical Code, equipment grounding is the grounding of non-current carrying metal parts of equipment, raceways, and enclosures. System grounding is the intentional grounding of one conductor of a three-phase system or of the neutral conductor of a single-phase system. A current-carrying conductor is a conductor intended to carry current in normal operation. A non-current carrying conductor is a conductor not intended to carry current in normal operation. Ground is the earth or any conducting body that serves in place of the earth. Grounded means connected to the ground or to a ground conductor. Grounding is the act of connecting a system or circuit to ground. Neutral is the midpoint of a three-phase transformer secondary or generator winding. A neutral conductor is a conductor connected to the neutral point of a system and intended to carry only unbalanced currents. A grounding conductor is a conductor used to connect equipment or the grounded circuit of a wiring system to a grounding electrode. A grounding rod is a metal rod driven into the ground and used as a grounding electrode. A grounding plate is a metal plate buried in the ground and used as a grounding electrode. Philippine Electrical Code does not define all of the terms listed previously. Understanding these definitions is crucial for electrical safety and proper installation. Grounding and bonding ensure a safe path for fault current, protecting people and equipment. Firstly, consider the differences between grounding and bonding. Grounding provides a path for fault current to return to the source, tripping a circuit breaker or fuse and de-energizing the circuit. Bonding, on the other hand, connects conductive parts together to equalize their potential, minimizing the risk of electric shock. Secondly, it's important to distinguish between system grounding and equipment grounding. System grounding involves grounding a specific point of the electrical system, such as the neutral point of a transformer. This helps to stabilize the voltage and limit overvoltages. Equipment grounding involves grounding the metal parts of equipment, enclosures, and raceways to provide a low impedance path for fault current. Thirdly, the role of conductors must be clarified. Current-carrying conductors are those that carry current under normal operating conditions, such as the hot and neutral wires in a circuit. Non-current carrying conductors are those that do not carry current under normal conditions, but may carry current during a fault, such as the equipment grounding conductor. Fourthly, grounding electrodes are essential components of a grounding system. Grounding rods and grounding plates are common types of grounding electrodes that provide a connection to the earth. The resistance of the grounding electrode is an important factor in determining the effectiveness of the grounding system. The NEC recommends a maximum resistance of 25 ohms for a single grounding electrode. If this resistance cannot be achieved, multiple grounding electrodes must be installed. The minimum spacing between grounding electrodes is 6 feet. However, a greater distance may be required to achieve the desired resistance. In areas with high soil resistivity, it may be necessary to use more than 2 grounding electrodes, or to use ground-enhancing materials to reduce the resistance. The Philippine Electrical Code also addresses grounding and bonding requirements. While there may be some differences in terminology and specific requirements, the basic principles are the same. It is important to consult the applicable electrical code for the specific requirements in your area. Proper grounding and bonding are essential for electrical safety. By understanding the definitions and requirements outlined in the NEC and the Philippine Electrical Code, you can help ensure a safe and reliable electrical system. Remember to always consult with a qualified electrician for any electrical work. In addition to the definitions and requirements, it is also important to understand the purpose of grounding and bonding. Grounding and bonding are intended to protect people and equipment from electrical shock and fire hazards. By providing a low impedance path for fault current, grounding and bonding help to ensure that circuit breakers and fuses will trip quickly, de-energizing the circuit and preventing further damage. Grounding and bonding also help to reduce the risk of static electricity buildup, which can damage sensitive electronic equipment. In summary, grounding and bonding are essential components of a safe and reliable electrical system. By understanding the definitions, requirements, and purpose of grounding and bonding, you can help ensure that your electrical system is properly installed and maintained. Always consult with a qualified electrician for any electrical work and follow all applicable electrical codes. There are various types of grounding systems. The most common types are solidly grounded systems, impedance grounded systems, and ungrounded systems. Solidly grounded systems are those in which the neutral point of the transformer is directly connected to ground. These systems are commonly used in residential and commercial applications. Impedance grounded systems are those in which the neutral point of the transformer is connected to ground through an impedance, such as a resistor. These systems are often used in industrial applications where it is important to limit the ground fault current. Ungrounded systems are those in which the neutral point of the transformer is not connected to ground. These systems are sometimes used in critical applications where it is important to maintain power even during a ground fault. Each type of grounding system has its own advantages and disadvantages. The choice of grounding system depends on the specific application and the desired level of safety and reliability. Proper selection and installation of the grounding system are critical for ensuring electrical safety and equipment protection. In addition to grounding, bonding is also essential for electrical safety. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault current. This includes metal enclosures, raceways, and equipment frames. Bonding helps to equalize the potential between different metal parts, reducing the risk of electric shock. Bonding is typically accomplished using bonding jumpers or bonding conductors. Bonding jumpers are short lengths of wire that are used to connect metal parts together. Bonding conductors are longer lengths of wire that are used to connect metal parts back to the grounding electrode. The size of the bonding jumpers and bonding conductors depends on the size of the circuit and the available fault current. Proper bonding is essential for ensuring that fault current will flow back to the source, tripping the circuit breaker or fuse and energizing the circuit. In addition to the NEC and the Philippine Electrical Code, there are other standards and guidelines that address grounding and bonding. These include the Institute of Electrical and Electronics Engineers, IEE, Standard 142, also known as the Green Book, which provides recommendations for grounding and bonding of industrial and commercial power systems. There are also various industry-specific standards that address grounding and bonding requirements for specific types of equipment and installations. It is important to be familiar with all applicable standards and guidelines when designing and installing electrical systems. In addition to the technical aspects of grounding and bonding, it is also important to consider the human factors. Electrical safety is a shared responsibility. Everyone who works with or around electrical equipment should be aware of the hazards and take steps to protect themselves. This includes wearing appropriate personal protective equipment such as gloves and safety glasses, and following safe work practices. It also includes reporting any electrical hazards to the appropriate authorities. By working together, we can create a safer electrical environment. Finally, it is important to remember that electrical codes and standards are constantly evolving. It is important to stay up to date on the latest changes and to consult with a qualified electrician or electrical engineer when designing or installing electrical systems. Proper grounding and bonding are essential for electrical safety and equipment protection. By understanding the definitions, requirements, and purpose of grounding and bonding, you can help ensure that your electrical system is properly installed and maintained. Remember to always consult with a qualified electrician for any electrical work and follow all applicable electrical codes and standards. The correct installation and maintenance of grounding and bonding systems involve several practical steps. Firstly, visually inspect grounding and bonding connections regularly. Look for signs of corrosion, loose connections, or damaged conductors. Secondly, use appropriate tools and techniques when making grounding and bonding connections. Ensure that connections are tight and secure. Thirdly, test the resistance of the grounding electrode periodically. The resistance should be no more than 25 ohms. If the resistance is higher than 25 ohms, take corrective action, such as adding additional grounding electrodes or using ground-enhancing materials. Fourthly, document all grounding and bonding connections. This will help with troubleshooting and maintenance. Fifthly, provide training to employees on proper grounding and bonding procedures. This will help to ensure that everyone is aware of the hazards and takes steps to protect themselves. Sixthly, follow all applicable electrical codes and standards. This will help to ensure that your electrical system is properly installed and maintained. Seventhly, consult with a qualified electrician or electrical engineer when designing or installing electrical systems. They can provide expert advice and ensure that your system meets all applicable requirements. Eighthly, be aware of the specific grounding and bonding requirements for different types of equipment and installations. Some equipment may require special grounding or bonding techniques. Ninthly, use only approved grounding and bonding materials. This will help to ensure that the materials are compatible with the electrical system and will provide adequate protection. Tenthly, maintain a clean and dry environment around grounding and bonding connections. This will help to prevent corrosion and ensure that connections remain tight and secure. By following these practical steps, you can help to ensure that your grounding and bonding systems are properly installed and maintained, providing a safe and reliable electrical system. Understanding the NEC tables related to grounding and bonding is crucial for proper installation. NEC Table 250.66 provides the sizing requirements for grounding electrode conductors for alternating current systems. This table is used to determine the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. NEC Table 250.102 C1 specifies the sizing requirements for bonding jumpers and system bonding jumpers. This table is used to determine the minimum size of the bonding jumpers based on the size of the service entrance conductors or the derived phase conductors. NEC Table 250.122 provides the sizing requirements for equipment grounding conductors. This table is used to determine the minimum size of the equipment grounding conductor based on the rating of the overcurrent protective device protecting the circuit. NEC Table 310.16 provides the allowable ampacities of insulated conductors. This table is used to determine the maximum current that a conductor can carry safely based on its size, insulation type, and installation conditions. When using these NEC tables, it is important to follow all applicable notes and instructions. The notes provide additional information and clarification on how to use the tables correctly. It is also important to consult with a qualified electrician or electrical engineer to ensure that you are using the tables correctly and that your electrical system meets all applicable requirements. The effective ground fault current path is the intentional low impedance electrically conductive path designed to carry fault current from the point of a ground fault on a wiring system back to the electrical source supply. Ground fault current must have the capacity and be of sufficiently low impedance to facilitate the operation of the overcurrent protection. If the current doesn't return to the source, the circuit breaker will not trip to open the circuit. Parts of the effective ground fault current path are the equipment grounding conductor, the grounding electrode conductor, and the neutral conductor. The earth itself is not considered an effective ground fault current path. The impedance of the earth is too high to allow sufficient current to flow to trip a circuit breaker.